everyone, I'm Chekene, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on FEMA P-2018, Seismic Evaluation of Older Concrete Buildings for Collapse Potential. This webinar is brought to you by the Applied Technology Council under a contract with FEMA, the Federal Emergency Management Agency. If you haven't already, you can go ahead and download the handouts using the link that was provided in the chat. We know that many of you are interested in receiving professional development hours for your attendance today. So know that if you are registered and attending this webinar live, a certificate documenting professional development hours will be sent to you by email within 4 weeks. If at any time during the webinar you have questions, please go ahead and type them in the Q&A. We will not be having a live question and answer session during this webinar, but we will provide you with written responses to all technical questions that we received today. One of our instructors will actually be responding to as many technical questions in writing through the Q&A portal during the presentation, but it's unlikely that she will get to all of them. So if Abby doesn't get to your question, just know that you will receive the response to your technical question after the webinar. Next, I'd like to turn it over to Patia Scott from FEMA's Earthquake and Wind Programs branch. She will be providing a brief introduction to today's webinar. Patia, please go ahead.
Thanks, Kira. Good afternoon. My name is Patia Scott, and I'm a civil engineer for the Federal Emergency Management Agency's Earthquake and Wind Programs branch. It's my pleasure to welcome you to today's webinar on assessing the collapse risk for older concrete buildings. A little bit of background on this. FEMA has the goal of reducing the ever-increasing costs that disasters inflict on our country. Addressing this risk presented by our population of existing buildings is the most effective way of reducing the costs of future disasters. As part of its responsibilities under the National Earthquake Hazard Reductions Program, FEMA is charged with supporting the investigation of seismic technical design issues, the development, publication, and dissemination of technical design and construction guidance products, and the support of training and related outreach efforts like this one. One of the issues of significant concern for the program is the risk presented by older, seismically vulnerable concrete buildings known as non-ductile concrete buildings that were built prior to the mid-1970s. One of the key lessons to come out of the 1971 San Fernando earthquake was the performance of concrete frame buildings, and that design codes of the era did not provide for significant or sufficient steel reinforcing. By the mid-1970s, design codes had increased the amount of detailing of steel reinforcing to prevent this type of failure. However, buildings constructed to the older codes still exist in great numbers and pose significant risk. While we have developed retrofitting criteria for seismically deficient non-ductile concrete buildings, the problem remains one of efficient identification of the most hazardous buildings so we can better focus our limited resources. While not all pre-1970s non-ductile concrete buildings are equally hazardous, it is often difficult to visually determine which of these buildings would be collapse hazards and which are not. FEMA P-2018 provides a simplified methodology for evaluating collapse resistance using simplified estimates of drift demand. Development of the procedures included testing of the methodology by practicing engineers in several rounds of trial evaluations and vetting of the methodology in a series of annual workshops. We hope you will find this webinar useful and encourage you to let us know if you have any questions. And we also want to thank the Applied Technology Council for helping us put on this session. Back to you, Kira.
Thank you so much, Patia. So now I'll tell you about our two fabulous presenters today. First up is Bill Holmes, who worked as a structural engineer for Rutherford and Chekene in San Francisco for 45 years before retiring in 2010. Since then, he has primarily worked on studies and technology transfer for the Applied Technology Council, National Institute of Building Sciences, and the Building Science Safety Council. He was the senior consultant for ATC 33, which became ASCE 41, and he was the project technical director for development of FEMA P-2018. He is a member of the National Academy of Engineers. Our second presenter today will be Abbie Liel, who is a professor in the Department of Civil, Environmental, and Architectural Engineering at the University of Colorado at Boulder. She is the author of over 80 peer-reviewed journal articles, including many about non-ductile reinforced concrete buildings, assessment of their risk and collapse potential. As a member of the Project Technical Committee, she greatly contributed to the development of the FEMA P-2018 guidelines. Abbie is a licensed PE and has been the recipient of multiple awards, including the Shaw Family Innovation Prize and the University of Colorado College of Engineering Memorial Teaching Award. I would now like to turn the webinar over to Bill. Bill, please go ahead.
Thank you. I'll give you another welcome to this seminar. This is going to be a little fast and furious because there's a lot of material. So Abbie and I are going to try to give you an overview of this methodology. The webinar handouts was mentioned. Among the handouts is the book itself, all the webinar slides, an example, a real live example application onto a building. And the one in the middle there, guidance for implementation, is a document that ATC produced as a result of San Francisco trying out the methodology on 5 buildings with engineers. And of course, they had some questions. Most of these are clarifications. We didn't really change anything in the document, but anybody who is going to implement the methodology, that will be useful. So today, I'm going to give an introduction and overview of the document, and then I'm going to talk about the demand side, and Abbie's going to talk about the capacity side. It turns out drift of the building is the major contributor to collapse. So this whole methodology is based upon looking at the drift demand in a simplified method, comparing it with the drift capacity, and that allows us to come up with an approximation of the risk of collapse. So then after I finish the demand, Abbie will talk about the capacity side and also talking about some building types and an example that is available. And then I will wrap it up with some policy issues. So again, we'll start with this introduction and overview. First of all, what are we trying to do today? Well, we're trying to explain what buildings are included with this method and which buildings would not be included because the method may not apply. What can you expect to get from this analysis? What is in the book, actually? It's a big book, a lot of chapters, a lot of appendices, and we'll try to quickly explain what's in there. And then, of course, as we go through this, we'll give an overview of the methodology itself, but certainly not in enough detail for you to tomorrow trying to implement it. There were many participants. This went on for 7 years. A lot of FEMA people, Applied Technology Council. We had a project technical committee that Abbie and I were on, along with Mike Moraine, Jack Maley, and Peter Summers. We also had a lot of students that helped out with a lot of the analysis, and we had a very big and good project review panel that met 10 times and gave us input. So why do we have this document? Well, it was spoken a little bit in the introduction, but back in a little history in 2005 and 2006, there was a thing called the Concrete Coalition. It was a bunch of engineers who were interested in this problem of older concrete buildings and concerned that nobody was really doing much about it. So they started some initiatives, including trying to devise methods of giving inventory. That's one of the biggest problems, is how many of these buildings are there and where are they? So the Concrete Coalition also, figured out that, as was said before, not all of these buildings are collapse hazards. So how do we try to sort out which ones are hazardous and which ones are not? There are seismic evaluation methods available, specifically ASC 41, but they're basically pass-fail. You either pass the methodology or you fail. It's really hard to come up with priorities of which buildings are worse than others. But in terms of an ordinance, FEMA and many people didn't think it was practical to automatically require all these buildings to be fixed at once, when in fact there's a large variation in risks. So it was concluded that a method to measure the relative risk was needed to rank the buildings in any inventory. So this is the epitome of what we're calling an exceptionally high-risk building. This was actually a two-story building originally. The first story is completely gone, and that story collapse is precisely what we're trying to predict in terms of risk. During the development of the methodology, we had several different ideas of how we could measure this risk or how we could rank buildings. But right now, in the final methodology, the ranking of the risk is related to the probability of a building collapse, which we're basically defining as a story collapse. The ratings, in fact, go in tenths from 0.1 to 0.9. We also have a simplified scale where the 0.1 to 0.9 is broken into three categories. Greater than 0.7 is exceptionally high risk. The 0.1 and 0.9 roughly equivalent to the probability of collapse in the target event. So when you start this, the jurisdiction or owner, whoever you're doing it for, has to decide what event you're going to test. We're not intending to override ASC 41, which has a pass-fail of established consensus over many years. And this method is brand new, so we haven't coordinated it with ASC 41 as yet. The length of time that it takes to perform one of these analyses, of course, it varies a lot with the size of the building, but it's about 160 engineering hours. Some of the things we had to consider when we were trying to invent this method was, how do buildings collapse? Well, the most obvious thing is column failure. This has been the cause of many collapses. This is the lack of proper reinforcing in the columns. This was a gravity column collapse. That's why we have to consider all gravity elements in this methodology, not just the lateral force resistance system. On the left, these were gravity columns that collapsed in this garage and literally pulled the perimeter inward. And joints are also causes of failure. They can cause mechanism. So here's some examples of that. And of course, many people during the development of methodology thought that wall buildings were so safe that we didn't really have to include them, but there certainly are examples. This is a wall building in Chile that failed at the base and basically fell over. This is another wall building in New Zealand that the walls were toward the center of the building and they collapsed and pulled the building inward. Many people were killed in this building. So how are the ratings done in general? Well, we estimate story drift demands from the selected ground motions with approximate methods. We then compare those drift demands on all gravity supporting vertically oriented elements with the drift capacities. So we get that DC ratio. That's including on columns, the slab column punching shear if you have a column slab frame, for walls, and for infill bays. The capacities in all these cases are based on the probability of loss of gravity carrying ability based upon available tests. There have been many laboratory tests of all of these elements, and many different people have analyzed those tests and come up with risks of collapse based upon proportional to the drift demand. So then we estimate the probability of collapse of the story of the element based on its ratio, and then all of those probabilities of collapses of the elements are combined, and Abbie will talk about this a little bit more, to get the estimate of the one-story collapse, which becomes the rating. The highest story rating is the rating of the building. And again, as I said, it's rounded to a tenth, and that's the rating of the building. So how is this different than ASC 41 for those of you that are familiar with 41? Well, 41 is a national standard for seismic evaluation and retrofit and covers all materials and building types. P-2018 was very specifically aimed at older concrete buildings only. The analytical methods of ASC 41 are component-based, meaning that you're always dealing with what is the seismic demand and capacity of an individual element, like a beam or a column or a wall. Whereas P-2018 results on a global basis, measuring the risk of the whole story collapsing. 41 can measure several damage states. It has different performance levels called occupancy or life safety or collapse prevention, whereas 2018 is focused only on the danger from collapse of one of these older concrete buildings. 41, for many buildings, nonlinear analysis is suggested or even necessary to obtain realistic and non-conservative results. Nonlinear concepts are built into this methodology of P-2018, and the methodology is intended to get more consistent results in less time without actually doing the nonlinear analysis. The organization of the document is in chapters. As you can see here, the first 4 are basically introductory material, things that you should be aware of and things you should do before you really start. Chapter 5 we call the hub of the methodology. That's where you really get into looking at what type of building that you have, because this methodology is separated into frames, wall frames, bearing walls, and infill frames. So after you get through that chapter 5, depending upon which kind of a building, you go to one of the appropriate chapters to finish the analysis. Then finally, chapter 10 kind of wraps it up and integrates the simplified ratings that you might get with the detailed ratings. And of course, there's now many appendices. These appendices contain the background information that we developed during the development of the methodology. And I'm not going to go through all these, but if you get interested in how the heck did they do that, you can generally find those answers in these appendices. So again, let me go through the chapters quickly. Chapter 1 is purely background and introductory material. It has little to do with the methodology. Chapter 2 talks about what kind of buildings need to be covered and emphasizes that it's not only the lateral system, but also the gravity system that has to be considered. So what buildings are applicable? Well, pure frame buildings, which have a beam column gravity and lateral system, or a slab column gravity and lateral system. So many of these buildings have no lateral system at all. They're just gravity systems. Then we have frame wall buildings, which include both types of frames, but that have shear walls or other walls that maybe weren't intended to be shear walls, but turn out to be shear walls if they're made with concrete. And then, of course, we have bearing wall buildings that consist of only walls and slabs. There are some of those buildings mostly residential. And then finally, we have masonry infill frame buildings, which are typically concrete frames where the perimeter is infilled with masonry. Not applicable. Well, there's buildings that don't have an adequate load path. This methodology depends upon an analysis of the building and follows the loads from the lateral loads caused by the shaking into the elements that are resisting them. If there is no load path, the method won't work, and the building should be considered a high risk in any case. And then we're not covering flexible diaphragms. There are several building types that are existing that, for similar reasons to these two, would not be covered, and those specific building types are listed in that chapter. Chapter 3 is the general requirements. We're basically suggesting, well, you have to have drawings or detailed knowledge of the structure because you're basically doing analysis work. So you have to have the size of the concrete members and the reinforcing. Typically that requires original drawings. We are well aware that that is a problem in many cases with older buildings, but the fact of the matter is, if you're going to come up with any kind of analysis and that generates a risk of collapse, you basically have to know the details of the strengths and deformation capacity of the building. We suggest, of course, a site investigation to make sure the building is still there and also confirm that the drawings you have are reasonably correct. ASC 41 has a lot of guidance about existing buildings, and because you often don't know what the materials are, they have default material properties that are dependent upon when the building was built. We are not requiring physical testing. We are suggesting using the default material properties from 41 if you have no other guidance. Again, I said you need a complete load path. Many people have always said this. We have actually put some meat on that bone by trying to give some guidance about what we think a complete load path consists of. And then, of course, Chapter 3 talks about what seismic hazard you should use. You should obviously use the same hazard for all buildings that you're testing. And there is a lot of seismic hazard defined in 41, and we're suggesting something that they define as BSE 2E for this methodology. Chapter 4 has component strengths. It's very important to read this before you start Chapter 5 because it's slightly different than ASE 41 for you, those of you who are familiar with 41. These are some examples of how we've changed things. The structural demands and capacity are at median and so on. I won't go through these, but you should look at this chapter before you get started. As I mentioned before, Chapter 5 is really the guts of the methodology. And the first section goes through the various building types. These structure types are important because the structural period, vibration period will change. Then the methods to get it change depending upon what building type it is. And of course, that leads to the story drift determination, which is one of the two primary parameters that we're looking for. Then this chapter also includes an effective yield strength, which we're getting with a mechanism analysis, which is sort of a simplified pushover analysis. And it's a standard structural engineering analysis, but that will lead you to the lateral strength of the building and the period and eventually the displacement demand. Once you get out of Chapter 5, you go to the actual story collapse calculations that are in Chapter 6, 7, 8, and 9, depending upon whether you're a pure frame or a frame wall or a bearing wall building or infill building. The typical flow of all those chapters are to use the effective teeth that you got from Chapter 5, and you have a site spectra, so you can calculate the spectral displacement, very similar to ASE 41. You then calculate the story drifts based upon that spectral displacement, which is the displacement of an equivalent single degree of freedom system to your building. But we have tabularized story alpha factors that allow you to sort of distribute that spectral displacement into the stories, which is where you start your calculations of the comparison of the demand and capacity ratios. You then calculate the column and all other gravity elements drift capacity, and then you have a demand capacity ratio of all the gravity elements in the system, and you can get the collapse rating based upon a methodology developed in this project based upon the probability of collapse of all the gravity supporting elements based upon these drift demand capacity ratios. These are then converted. These individual ratings are converted to a story rating based upon the probability of those gravity elements losing 25% of the loss of gravity support of the story. Now that 25% is somewhat arbitrary. We looked at different levels, 35 and 20 and so on, and we found that the priority between buildings, or the collapse probability between buildings, the ratings didn't change much. So we stuck with 25%. So then Chapter 10, as I said, puts all together, and you either have an early out, which I'll describe in a minute, which puts you in one of these three general categories, or if you've gone through the whole methodology, you would end up with a number from 0.1 to 0.9. So you'd have basically 10 variations instead of 3. The priorities can then be set based upon those numbers. Obviously, the highest rating should be the highest priority to fix. So that's the overview. Now I'm going to talk about how, on the demand side, how do you approximately get the demands, and then after that, Abbie will talk about how you get the capacities. So as I mentioned, you get the demands from a simplified mechanism analysis. Then that will lead you to getting the lateral strength, which is very important. We find that all deficiencies have a difference in probability of collapse depending upon the lateral strength of the building. So that is a very important parameter. We get the period, the effective period. That gives us the global demand to capacity ratio, which is a very important parameter for the whole building, and eventually get the displacement demand. So just some simple definitions. The base shear strength under static lateral loading is considering expected member strengths calculated along each principal direction. So you have to do this analysis in both directions. The method is a simplified mechanism analysis, which I will explain. Or if you have a pushover, otherwise known as a nonlinear static analysis, you can use that and substitute that into this method. But if you're starting out looking at a building for the first time, seldom will you have a nonlinear static analysis. If you're looking at a building that has been analyzed before, there might be such an analysis available. So again, we have some definitions that are needed to describe the mechanism analysis. These are pretty standard definitions. FX formula there is a standard way to distribute earthquake forces over a building. It basically is an inverted triangle, as you can see in the upper left. And this tells you which is story one and which is level one and so on. This is pretty standard stuff. So we have several mechanisms. The first one is what is commonly called a soft story. It's really more of a weak story, but this is when you assume that one story, it could be any story, but typically it's the first story, ends up with a mechanism. In other words, it will move horizontally. That mechanism is can most commonly be understood by saying, well, if there's a hinge at the top and bottom of every column, then obviously that's a mechanism the building will move horizontally. Now, using the principles of virtual displacements and external work equaling internal work, it's pretty easy to develop simplified equations for this. So we have done this for you. So if you've forgotten how to do a mechanism analysis, we are giving you the formulas. And what you're looking for is a mechanism that is the weakest one. So if you push on the building, which mechanism would occur first? That's what we're looking for. So you're testing the mechanism, the strength of each of these common mechanisms. So mechanism one also has a complexity that the elements in that story could either fail by flexural hinges at the ends or by shear failure. And there's very common methods to determine whether a column or a wall is what we call shear critical or flexually critical. And the control and strength would depend upon those comparisons and those calculations. But when all is said and done, and you get the capacity of every vertical element in the story, you simply add them up, and you can convert that to get this DP1, which is the base shear strength of the building. Mechanism two is a different mechanism. That is a mechanism when, rather than the displacement or the mechanism occurs in one story, it basically occurs over the whole height of the story. And typically you can see on the left, this commonly occurs if you have weak beams and you end up with a flexural hinge at each end of each beam. It also occurs many times in wall buildings where the wall forms a flexural hinge at the base, but from the base to the top, the wall stays relatively rigid and it forces all the other stories to have approximate equal displacements. So again, in these two cases, we give formulas for how do you get DP1, which is the number you're looking for. And after you have run several of these mechanisms, you're trying to find the weakest one. Now, most engineers can look at a building and probably figure out which of these mechanisms they should concentrate on. But if you can't, then you might have to run all of the mechanisms. Mechanism three is similar to mechanism one, but it occurs on an upper story. And there's some slightly different formulas there, because once you get the capacity of that story, you have to convert it down to a base shear at the ground. And again, we give the formulas to do that. And then mechanism four is parallel to mechanism two, but it also occurs at an upper story. And this normally happens when there's a discontinuity, as shown there. There's a very strong wall and it gets half as big. And at that level from above is where mechanism 4 would form. So you would look for discontinuities in buildings that might cause this, and you might check this mechanism. Now, all of these pictures are frames, but of course, this is really a three-dimensional problem. So the strength of the base shear is the sum of all the frames in each direction. So it's really a 3D issue, and you have to calculate a comparable mechanism in each frame in order to get the total mechanism strength and find which one is minimum and governing. So once you have that, you have the effective yield strength. So at that point, you can get the effective fundamental period, because in fact, we have done a bunch of analysis, and what we're looking for is the effective period at some level of deformation. That curve there is what's commonly called a pushover curve. As the lateral forces get bigger, the horizontal is how far is the building displacing, and the typical elastic period is the slope, K slope at the very base of the building before it's damaged. And of course, as the building leans over, that K gets softer and softer. So how do you know which one to pick? Well, ASC 41 has figured that out. And there is a methodology in there, if you have a pushover, of how you get that curve. But we're assuming you don't have a pushover. So we have done a lot of analysis in order to come up with formulas for the period on the various building types. So here is what we did for frames. This little picture at the lower left, the period is on the left, the height of the building on the right, and the various dots, like the orange dots, are a building strength of 0.05 W. And then at the bottom, it's 0.25 W. So the very strong buildings are at the bottom. Very weak buildings are at the top. The two lines are the ASC 41 formula and the ASC 7 formula. So you can see those formulas are intentionally very stiff, very short period, because they're looking for the biggest forces, whereas we're looking for the biggest possible displacements. So we want more realistic periods that are longer. And you can see how heavily dependent the period that we're looking for is on the strength of the building. So the formula we come up with is here, and you can see Vy over W is basically the base shear strength as a proportion of W. And so this is for frames. We wanted to check, sanity check here. This graph here is a famous one, data from Goel and Chopra. They went out and measured real periods of buildings. Every one of those dots is a real building. And you can see where our curves land with the strength getting stronger and stronger as you go down. So very strong buildings are right sort of in the middle of the Goel and Chopra, and as they get weaker, they go up. So we think that that formula is a good representation, a simplified way to get the period for frame buildings. For wall and wall frame buildings, that will not work. So we actually borrowed another formula from Goel and Chopra that is in ASCE 17716, but we changed it because we want to reduce effective stiffness. So there are some minor changes, but this formula is for wall and wall frames. For other buildings, pier spandrel buildings and infill frame systems, there's yet another way to get the period. So that's why it's so important to pick to get your building identified as to what type of frame or what type of concrete building it is. So we get the period, and for those of you who have done any kind of seismic analysis, the period you can put on a spectral plot and end up with a spectral acceleration. So on the right, you take your period and you go up to where you hit the response spectra, and you get a SA, which is a spectral acceleration. You can divide that by the base shear of the building and get something that's defined in ASC 41 as mu strength. So that's kind of a global demand capacity ratio, because SA is the global demand in acceleration on the building, and BY is a global strength based upon mechanism analysis. So this mu strength is an important parameter, because, as I say, the strength has shown in our studies to be very important for the risk of collapse. So once you get that new strength, we found that there are some tendencies that we could find that would enable us to not have to go through the whole procedure. If you have an extremely low new strength, that means that your demand and capacity is almost equal. Well, if the demand and capacity is almost equal, that means like the building is probably almost elastic. So if the building is almost elastic in the demand event, it probably is not much of a risk of collapse. So we have two cases there, one with shear critical columns. We don't like shear critical columns much. So that requires a mu strength of 0.75, but all other cases, if you have a mu strength of 1.5, we think you can consider yourself lower seismic risk and not go through the procedure. On the other end of the spectrum, you've got exceptionally high risk buildings, and we found that frames with shear critical columns, if you get over a mu strength of about 2, you could be in trouble with collapse. Frames without shear critical columns, we can go all the way up to a mu strength of 5.5 before we become concerned. There's also some discontinuous wall conditions in here, which I can't get into. So here's a little poll. Mu strength is an important parameter in P-2018 because, and there are several things here, and we want you to choose all of the things that are true. It's a hint, there's more than one.
Great, Bill. And the poll is open, so people are responding. Great, and it looks like about half of people have responded so far. So I'm going to leave the poll open a little bit longer because I know this is a bit of a long poll question to read. All right, it looks like the responses are flattening out a little bit more. So I'll give everybody another 10 seconds or so to get in your responses. All right, I'm going to go ahead and end the poll, Bill.
Okay.
And I'm sharing the results now. Can you see them?
Okay. Yes, I can.
Wonderful.
Lateral strength has a large influence on collapse. That's true. A lot of people pick that one. It's a measure of global demand capacity ratio. That's true. We have some people who think a Greek letter is important, but that's not right in this case. It may be important, but not in this case. Global strength affects the collapse probability. True. And that rough parameters of that last one is not true. That's just a made up thing. So I think people were paying attention. I appreciate that. So we'll move along here.
Great, so I just closed the poll.
Okay. So we go into story drift calculations after we get through chapter 5, when we had that drift calculation. So I'll go quickly through this. What you've gotten is from the response spectra is the drift of an equivalent single degree of freedom system. So your complex building is reduced down to a lollipop. And this formula comes right out of ASC 41 as a standard formula to get the drift of a single degree of freedom system based upon that spectral acceleration and the effective period and some G and 4 pi squared, so on and so forth. There's some coefficients that come out of ASC 41. It's just formulas that you can plug and chug. So you get that, it's very important to get that spectral drift. So now we have to figure out how much of the spectral drift goes to each story. So we have done that for you. We have come up with this alpha factor in a table, and depending upon the height of the building, the first column of the table is the number of stories. Then you determine which of the yield mechanisms that you're dealing with. And then there's an alpha factor. Here is 2, which would say that you put alpha in that formula, and you're basically giving a proportion of the spectral drift that would go to the given story. So we've done this by doing thousands of calculations of various buildings and have come up with these alpha factors to help you do this. So there's a couple of drift adjustments. One is for P delta. That only applies to frame systems. We don't think that P delta is very important for walled systems. So for frame systems, you have to take this story drift that you have calculated and amplify it through this formula for P delta. Similarly, for wall buildings, although P delta is not important, torsion is. So for wall buildings, we have a torsional amplification that is applicable to wall or frame wall buildings. And again, it's a reasonably simple calculation. It's computationally large, but it's pretty simple. You basically have a center of mass and a center of strength, and you do some calculations about the torsion and the demand, and you can convert the spectral displacement to the drift that is occurring at your column or your wall or wherever you are in the building based upon these simple dimensions. So for frame buildings, you've now used P delta. You have a drift demand on every column in the building or every column in the building. And for wall buildings, through this torsion, you have a drift demand for every column or every wall, because walls do cause collapse in the building. So you've got the demand side of the equation through a lot of calculations. Most people have developed spreadsheets for these calculations. So now you have to start figuring out what are the capacities. So Abbie will now take over and discuss that side.
Okay, so as Bill said, I am going to take us from the demand side, drift demands, to drift capacities, and then explore what the implications for those calculations in terms of the rating system that is kind of the basic output of the FEMA P-2018 methodology. So just as a kind of roadmap for what I'm going to talk about, this methodology actually has 3 different ratings that we talk about. We start at the component level, so we evaluate drift demands and drift capacities at the component level. We then move to a story rating, and then the story ratings are the basis for this building rating. In each case, the rating tells you about the probability or likelihood of failure. So at the component level, this is the likelihood of drift demand exceeding the drift capacity, and we're interested in the capacity, the drift capacity at which a component loses its ability to carry gravity loads, because that's our critical measure of what's basically holding the building up. And then the story rating is the likelihood that the story can no longer carry its gravity loads, and then finally we get that to a building rating. So before I talk about the capacities, I just want to emphasize a couple of additional sections in the methodology which are really helpful from a scoping perspective. So 6.2 and similar sections in the later chapters is really about identifying the critical stories. What that basically is telling you as the analyst or as the engineer is it's saying focus your energies on doing calculations for the components at these stories. And which story you need to focus on depends on the mechanism that you've identified based on the calculations that Bill showed. Once you know your critical stories, you need to go through and identify which components at that story are your critical elements. So this slide is attempting to show you the kinds of critical elements that this methodology considers. So we have critical columns. Those could be the thing that are holding up your building, and the failure of those could be making your building collapse prone. You could have problems with your slab column connections. You could have locations where you have potentially problems at both the column and the slab column connection, and we have a way of dealing with that. We also have concern with especially corner beam column joints or corner beam column connections. Bill showed some pictures of buildings that had damage to joints, and so we have a way of dealing with that. We are concerned about columns that are discontinuous and also wall segments that are holding up the building. So each of these critical components, if you identify them, is then the topic of the further analysis and calculations that I'm going to show now. Okay, so the next calculation that is involved are these component ratings. So as I mentioned before, component ratings represent the probability that drift demands exceed the drift capacity, and our drift capacity of interest is the capacity associated with the vertical or gravity load carrying capacity. For those of you who've taken a structural reliability class, this is kind of a classic structural reliability problem. You have some demand on your building. It is uncertain. That's what's represented by this probability distribution. You have some capacity, which is also uncertain. Where the demand exceeds the capacity, that's where we're concerned about. There's some probability of that happening. So in the slides that are coming up, I'm going to talk about how we get this median demand on a component and then focus most of my slides on this median capacity for various types of components, and then how that turns into a rating for the critical components that we are interested in. Okay, so I only have like one, maybe two slides on demands because Bill has really taken us all the way to story drift demands. There's just a few things that happen after you get to the story level that mean that the drift on one component that might be different than the drift on another component. One of those Bill already talked about, so that's where you get torsions. So that means that components along one column line or one frame line of the building might have a different demand than those along another line. And then we also separate drifts by the drift demand associated with each component. So let me show you what that looks like. And this is really important for frames where it is in the combined action of beam and column systems that together produce the story drift. And so we need to account for the fact that beams are taking some portion of the story drift demand, and how much depends on the building of interest. And so columns, in terms of when we think about column capacity, we only need to compare the column capacity to that portion of the demand that is not taken by the beam. So this column demand is going to be less than the story demand. And how much less depends on the characteristics of the building. And in particular, there's this table, and you can see throughout these slides we'll have table references and section references, but this table looks at the ratio of columns to beam strengths and then says how much of the drift demand is going to the columns in that situation. So you have at the bottom cases with strong columns, weak beams, very strong columns, weak beams, I should say. So in those cases, most of the inelastic action is in the beams. On the other end of the spectrum, you have kind of weak columns relative to beams, and in that case, we would expect most of the inelastic action, most of the drift to be in those columns. So this is kind of a simplified structural analysis that's allowing us to quickly estimate the drift demands in the components that we are interested in. Okay, so I promised that most of my slides were going to be about drift capacities. We have that list of critical components, and the methodology provides guidelines and tables and calculations for assessing median drift capacity of all of those different types of components. We followed a similar approach for all the components, critical components we're interested in, which is that we went to the experimental test database, and for some components there's a lot of testing done. We mined that data to get good median predictions of column deformation capacity, and those predictions account for the key differences among columns or between columns in different buildings that will give one column, for example, more deformation capacity than others. So in the case of columns specifically, there's quite a few examples of column tests that are out there. And so we went to that data, we gathered that data. For those of you who are familiar with AST 41, it's pretty much the same data set that was used to develop the parameters A and B, et cetera, in AST 41. And then we looked at that data set in relation to the important parameters for that influence rotation capacity. So we know that failure mode influences rotation capacity. So here we're worried about flexure critical versus shear critical columns. Columns with higher gravity or axial load tend to have less rotation capacity. And we also know that transverse reinforcement, right, which is a critical detailing parameter that has changed a lot in more recent codes, right, is one of the characteristics we're going to look at. So columns that have greater transverse reinforcement tend to have greater rotation capacities. Sorry. So what this looks like in the method is these equations. So again, these are the equations, but they are based on the data set. They fit the data set well. We're going for the median capacity. That's a really important part of this methodology, is that we aren't trying to build conservatism in at this stage, right? We're trying to get an assessment of risk fairly across all buildings without building in some conservatisms more in some places than others. So this is a median capacity. These equations, the format looks a lot like AST 41, but in some cases there's some differences to reflect the different goals of these documents. And you can see here, this is for tied columns, square tied columns. We also have a similar table for spirally reinforced columns, and it's depending on axial load. That's this parameter here. Transverse reinforcement, that's this parameter here, and distinguishing between failure mode. Once you've done that work, you have a drift demand from the calculations that Bill described, and a drift capacity from those equations, those tables for a column. And then we have this handy table here where it says based on the ratio of the drift demand for drift capacity for a particular column, it gives you a rating. So you'll see at the top of the table where demands are low relative to capacity, we have a low rating, a low probability of failure. At the bottom of the table where demands are much greater than capacity, we have a high rating, so a high probability of failure. And this table here is doing, I had that one slide where I had probability distributions, but this table is doing that probability calculation, that structural reliability work, so the engineer doesn't need to do that, although that is the basis for the values in this table. Okay, so that was columns, and then we proceeded to look at all those other critical components that I mentioned. So here we are talking about walls. So there have been a lot of reinforced concrete wall tests. A team at UCLA led by Professor John Wallace has worked very hard in recent years to develop empirical relationships, really focusing on the potential for walls to fail vertically, lose their ability to carry gravity or vertical load. So they had about, I think, 1,000 wall tests that they put together in a database from which they use to develop these relationships for drift capacity of walls. So just as some illustrations of what those relationships looks like, this is for flexure controlled walls. So again, for walls, we see that the anticipated failure mode matters, and there's criteria and guidelines in the document to help you distinguish whether you have a flexure controlled wall or a shear controlled wall. This slide is related to flexure controlled walls. It has on the y-axis here the drift capacity to that wall. On the x-axis, this parameter, lambda sub b, is a slenderness ratio. So it has to do with the length of the wall and the depth of the compression stress block. And the team at UCLA found that this was a very influential parameter in terms of explaining trends in drift capacity for walls. We also see an important trend with axial load ratio. So higher axial loads are having lower drift capacity, the same kind of thing we saw with columns. If that was flexure controlled wall here, this one is for shear controlled walls. For the shear controlled walls, the axial load ratio is by far the most important parameter. And so we see trends with drift capacity decreasing with increasing axial load. The wall rating table looks very similar to the column rating table. In fact, it's the same. It just has a different title on it. So again, here we have our measure of the demand to capacity ratio. Over here, we have the rating. Where your demand is high relative to your capacity, you get a high rating. Okay, so Kiara, go ahead.
Great. So I'm going to go ahead and launch our next poll. So this is a true or false question. A higher column or wall rating indicates worse performance. And the results are coming in much more quickly for this one. It looks like almost half of the participants have already answered. So I'll give everyone another 10 seconds or so to consider your response. All right, I'm going to go ahead and close it, Abby.
Okay.
All right, I'm sharing the results.
Okay, so we have about 2/3 of our respondents saying the answer to that one was true, and about 1/3 saying false. So this one is true. So the rating is related to a probability of failure or a probability of collapse. So a higher rating indicates something worse is happening. It's also, the higher rating also indicates a greater ratio of demand to capacity. So if you want to think in that context, higher demand to capacity ratio, higher probability of failure, higher rating. Okay. So if you'll recall from my slide on the types of critical connections we actually have a long list of things we're worried about besides columns and walls. One of those is slab column connections. Here we are really worried about those like flat slab column connections that do not have, sufficient bottom reinforcement, and so not only can you get punching, but we're worried about punching that will lead to a loss of gravity load capacity in the building. So here again, we went to the experimental data, collected that, looked at how the drift capacity here on the y-axis varies with key parameters. In this case, the key parameter is the gravity shear ratio. And we see as the increasing gravity shear ratio, we have a lower capacity of the connections. I also want to use this plot to make the point again that in this methodology, our line is this dashed or dotted line here. And we were really trying to hit the middle of the data set, and that's because we have a method that's kind of hidden in underneath all of the words in the book. It's probabilistically kind of consistent from beginning to end, and so we're really going for median values in these predictions of capacity. So we're trying to hit the middle of that data set. Of course, if as a user of methodology, you don't have to look at the data, you don't have to think about the probabilities, you just have to go to a table. Here we have that gravity shear ratio and then a drift capacity in terms of the height of the story. Okay, so those are some of the key components, types of critical components that you have, and the analyst then needs to get a rating for all of the components. So this is where a spreadsheet would really come in handy. I think Bill mentioned that, because those calculations I showed, for example, for a column need to be repeated for all of the critical columns, or the calculations for a flat slab connection need to be repeated for all the flat slab connections. So you end up not in fact with one rating, but with a whole list of ratings for these component ratings that then get combined to give you an evaluation of your story rating. Now, remember that this methodology does not require kind of a detailed nonlinear analysis. So we want to say something, the story rating is trying to evaluate risk of story failure due to seismic activity. And we have the information we have at our disposal are these column ratings. So what we did is we developed a method that uses essentially the average rating of your components and predicts the story rating based on the average rating of your components, all without having to do, the engineer needing to do a nonlinear analysis. So just very briefly, how did we do that? Well, we did a bunch of Monte Carlo, which is basically probabilistic experiments that looked at how a story rating depended on a set of column or wall ratings. So if you want to, I think a Monte Carlo simulation is really kind of a brute force kind of computer experiment that says like, well, what if I had, you know, a set of component ratings that look like this? What would my assessment of the story be? And then what if I had a set of components that look like this? What would my assessment of the story be? And then that's all summarized in this analysis in terms of this pink line shown here. But this is the summary of a bunch of underlying kind of probabilistic what if questions that we evaluated based on our understanding of the uncertainties and the probabilities of failure from those component ratings. In the methodology, though, this looks like a straight line, and it's pretty straightforward. So this CR is our component ratings. We're taking the average of those. This weighting factor is just weighting the components that are carrying more axial load more heavily, or more gravity load more heavily, I should say. There's then an adjustment factor that depends on the spread of component ratings. So if all the components are similar, there's a different adjustment than if they're more different. And then the story rating is simply 1.5 times this adjusted average minus 0.1. So again, there's a lot of probabilistic work in the background, but what the engineer actually needs to do is a set of relatively simple kind of weighted average calculations based on those component ratings. Okay, we're almost to the end of this section. So we have our component ratings. We get a story rating that represents the probability the story loses more than 25% of its gravity carrying capacity. And then the building rating is simply the maximum of the story rating. So that building rating is the measure that allows us to compare among these buildings. So I know that's a lot, and it's kind of hard to see how it relates to a real building. So what I have next is a summary of an example application of a frame building. If you are interested in all of the gory details on this example application, there is one of the handouts relates to this application and has more detail than I have time to present today. I do want to acknowledge that this work was done by Rami and Yangbo, who are engineers at IDS Group, and I'm grateful to be presenting their work to help ground this discussion in a real building. I'm going to focus my discussion on kind of chapter 5, which is the hub of the methodology, which says what kind of system you have, what strength, what period. Go through chapter 6 because this is going to be a frame building, so frame buildings fall in chapter 6, and then show the building rating that is produced by this analysis. Okay, so here's my building. This is a real building, 5-story 1960s era building. It has frames on 3 sides and a solid concrete wall on one side along the north side. So and we are going to evaluate only the north-south direction, which we are going to classify as a frame system. If you are evaluating a building, you do need to evaluate both directions, but we wanted to focus on one direction so we have more time to get into the details. So for this discussion, we're only doing the north-south direction. Okay, so this is our building. I did want to just give you a little bit more context for this building. So it is a frame building. In the interior of the building, it does have kind of a beam system in both directions, but these beams are quite shallow. And it also has these kind of relatively large hexagonal, spirally reinforced kind of columns. And so we're going to see, there's some things I want you to note here are these large spirally reinforced columns. We're going to see how that plays into the methodology. We're going to see these slender beams, how that plays into our assessment of this performance through this methodology, as well as the kind of more conventional beam column system on the exterior of the building. Okay, so I'm starting with the Frame system definition, I should note that there are chapters that come, this is obvious, there are chapters that come before chapter 5, and there is some work to be done in chapter 3 and 4 before you get to chapter 5, especially around determination of loads and of strengths. I'm skipping that for now because that's mostly in line with kind of an engineer's current workflow, but just know that I already know how strong my columns are, I already know what material properties, expected material properties I'm dealing with, and so I'm going into my example with that information already in my back pocket. Okay, so I'm going to try to calculate the strength of this building. Our strength calculations have this mechanism analysis which Bill defined. For this building, we really have 2 candidate mechanisms, and the first one is mechanism 1, and that has to do with the story mechanism at the first story. So to do the calculations for the story mechanism at the first story, I'm looking at the column flexural strength and the column shear strength. So the details of these calculations are also provided in the handout, so I won't go through all the details, but we will note here that the column shear capacity is 118 kips and the column shear flexure controls is 53 kips. So these are flexure critical columns. And you might not be surprised having seen that spirally spiral reinforcements, these are these flexurally critical columns. So that's one of the things that's going into this calculation. So we're looking at the flexural capacity of the columns, we're adding up all of those columns, and we get 276 kips for one frame line. There are 9 frames, they're not all the same, but if we add up the strengths of all the frames, we get 2,500 kips as the strength associated, or the capacity associated with mechanism 1. We then have to go to mechanism 2. So mechanism 2 assumes that columns have sufficient strength to force yielding throughout the building height. So we're looking at columns at the base and then beam capacities all over the height of the building. Here I want to remind you about the characteristics of those beams. So those are shallow beams. They don't have a lot of flexural strength. They also do not have longitudinal bars, bottom reinforcement that goes continuous into the joint, and so they actually have fairly small strength, moment strength in the direction where those bottom bars could pull out. So when we do the calculations, we sum up all the beam strengths and the columns over the height of the building and the column strengths, and we find that there's about 1,400 kips of strength in mechanism 2. Mechanism 1, we got about 2,500 kips. The lower governs, and so our estimate of the building strength is going to be based on mechanism 2, which is the one that we find that governs. And that's really determined by this weak beam, strong column arrangement, which we find even in this non-ductile concrete structure. So based on our findings, those calculations, we found that mechanism 2 governs. The implications for that are that the critical story is the first story. We calculate our total strength, and the ratio of the shear strength to the weight is about 10%. And that will go into our period calculations. Okay, so for a frame building, which this building is a frame building in the direction we looked at. The frame building, the period depends on that V over W parameter as Bill Holmes explained, and so we get about 1.9 second period. I did want to note again that this is an effective fundamental period. It's not an elastic period, so if this number feels a little large to you, it's because we're really representing an effective period when the structure is responding and it's heavily in the nonlinear range. Okay, so then we go to chapter 5 and we cross our fingers that we're going to find something that gets us out of the further calculations. And so we look at this again as a repeat slide that from what Bill had, but there are some things that if we found they were true would automatically classify the building as lower seismic risk and get us out early. There are some things that would automatically classify us as exceptionally high seismic risk and get us out early. We find that we don't qualify for any of these for this building, but this mu strength, which is a demand to capacity ratio, is 5. And it's pretty close to 5.5. So we're already thinking like, okay, well, I didn't qualify as exceptionally high seismic risk in chapter 5, but this is not looking like a great building. I'm already seeing that potentially overall weakness of this structure might be a problem. So I'm going to keep that in mind as I go into the subsequent calculations. Okay, so I'm going to go to chapter 6. Remember, the critical components and critical stories is going to help us do our scoping to determine what we need to do the calculations for. Mechanism 2, I need to focus on that first story, and I'm going to focus here on my columns and also my column, my slab column connections. Now you might be thinking, well, there were some beams in this building, and that's true, but those beams are so shallow they actually behave like a flat slab around that slab column connection. So we're going to check those two as some of our critical components. Okay, so I've identified my critical components and critical stories, and I'm going to go to my drift demand. Okay, so this is the same equation Bill already presented. I'm getting an equivalent single degree of displacement based on my demand in my period. If you do those calculations as shown here on this slide, we get an equivalent seismic drift demand of 16.9 inches for this building, and then we're going to see how that plays out in terms of story and component demands. Okay, so the alpha parameter in table 6-1 is really what enables us to move from a single degree of freedom system to this real building where drift concentrates more in some stories than others. Alpha is the parameter that represents that. In this case, we have a 3 to 6 story building, which was mechanism 2. And so I find myself with an alpha value of 1.5 in here based on this table. And then I plug that into this equation here. So I had an effective displacement demand, have a few heights that I need to plug in here, and I get that the displacement at story 1 is just about, displacement demand at story 1 is just about 9 inches or about 4% drift. It's a pretty big demand, and so we're going to see how that plays out in terms of the capacity. This is a frame building, so we do need to consider P delta, and you know, we got a relatively long period. We have a relatively weak building. So perhaps will not surprise you to learn that we get a pretty big amplification due to P delta. Okay, so we had that 8.9 inches on the previous slide. That was at the critical first story. We get this factor of 1.8 approximately, so an 80% increase due to P delta. And so that demand increases to 16 inches or about 8% drift. And that's because this building really is a weak and flexible, relatively weak and relatively flexible building, and so it is sensitive to P delta effects. Okay, at the component level, I need to figure out how much my story drift is going to my components. For my slab column connections, because of the location of a slab column connection, all of the story drift demand goes to those connections. But for my columns, remember, I'm going to be helped out from the beams. And in this particular building, I'm helped out a lot by the beams because those beams are so weak and so flexible that most of the inelastic demand is going to go to the beams in this case. So my columns only have to take 30% of the story drift demand, and that's the demand I'm going to use to evaluate the ratings for the columns. Okay. Drift capacities. Now remember, I'm going to have to repeat these calculations for every component at the story. So all of the columns at the first story and all of those slab column connections. So this is just one such column. I have my VP over VN ratio, which indicates that it's flexure critical. I have an axial load ratio. I have a transverse reinforcement ratio. Remember, these do have a fairly high level of transverse reinforcement with the spiral reinforcing. And so I get a column rotation capacity of about 6% plastic rotation. So that's, even though this is, you know, this is a non-ductile older concrete building, those columns actually have a lot of drift capacity, okay? So that's the columns. And I'm using this equation up here because of my axial load and because I'm flexure critical. We also have these slab column connections. We have a relatively low level of gravity shear that goes in here, about 0.13. And so we expect our drift capacity is going to be close to 4.5% drift. It's in fact 4.3. And we get about 8.3 inches of capacity in the slab column connections. We have about 12 inches of capacity in the column connections. Okay, so we're repeating this process then for all of the columns and all of the connections. We do also in this building have some corner beam column connections, which we think will be vulnerable. We didn't go through this in the detail, but we do have an equation in the methodology for that as well, which depends on the axial load of the column at the joint level. And so if we do those calculations, we get 12 inches or about 6.2% drift for those connections. Okay. So I need to repeat this calculation then for all of my different components. I'm getting a ratio of demand to capacity for each of those components. Typically for each location in the building, which is I'm getting a ratio of drift capacity, drift demand of 1.8 or 1.9. And this is driven by the slab column connection. So of the columns and the slab column connections are the same location, I'm taking the higher drift demand to capacity ratio, and that is driven by the slab column connections, not the columns themselves in this particular case. So I have 1.8 to 1.9. That means I'm in this row of the table. This is just kind of the typical case. And so I'm getting a column rating of 0.8. Okay, so behind this is a lot of spreadsheet work that the IDS group did. So they have all the calculations for all the different components, but then we're able to distill those into story ratings. So remember, my story rating is an average component weighting weighted by the gravity load each component carries. In this case, I get an average of 0.8. Remember, this is a probability of failure or likelihood of failure of that component. So things are probably not looking very good, right? We have 80% probability of failure. That's on the high side, or at least, high relative to some other numbers. We do this adjustment based on the coefficient of variation. It doesn't make much difference in this case, and we get a story rating of 0.9. Okay, so that means that under this demand, this building is at the high end in terms of likelihood of story collapse, because 0.9, the upper bound of this number is 1, so 0.9 is pretty close to the upper bound. Okay, the building rating is then the maximum story rating in each direction. Remember, I only evaluated each direction and only evaluated one direction, so this building gets a building rating of 0.9. Now I'm going to turn it back over to Bill to show what we can do with these numbers.
Thank you, Abbie. That example is fascinating, but it's a mouthful. There's a lot of calculations. We've had about 25 different samples done by engineers in 2 different phases, and they all developed their own spreadsheets. But it is a lot of calculations, but it's just linear calculations and strength calculations. So how does this fit into the problem of non-ductile concrete buildings? This methodology in itself can't make anything safe. Some owner or jurisdiction or somebody has to decide they're going to pay to run these calculations and decide to do something about it.
So Bill, could you put it in slideshow mode?
Sorry.
Oh, looks good. Thanks.
Okay. So again, these rankings are intended to give the significance of risk of collapse. So again, as I started out, I said there's a lot of these older concrete buildings, but not all of them are of equal risk. Some of them have a very small risk of collapse, and some of them, as Abbie just showed, perhaps have a very high risk of collapse. So this could be used by a jurisdiction that wanted to pass an ordinance, or by an owner of a large inventory of concrete buildings that wanted to know what is a priority, what priority should I put on fixing these buildings. So that is really the purpose of development of this methodology. So an example program is included in the book in section 1.4. And Los Angeles already has an ordinance. They may have developed it a little bit differently. San Francisco is in the middle of developing an ordinance. So every jurisdiction might develop things a little differently, but there's always an issue of priority. And of course, some people think the priority is how many people are in the building. You could combine the number of people in the building with the probability of collapse, for example, as one way to come up with a priority of getting these buildings fixed. So this is an example inventory. The rankings are at the bottom, the number of buildings, I just made this up, but you have 20 buildings at 0.2 and so on. So the red is an example of, there were a couple of buildings that had such a high mu strength that they were defaulted to exceptionally high risk. And the ones in blue, presumably you did the calculations and you came up with these numbers. A couple of buildings are 0.9, maybe 9 buildings are 0.7 and so on. So at some point, when enough of these calculations are done or enough buildings are tested, we might be able to make a judgment that below 0.3, for example, these buildings are no more risky than any other building, and maybe they don't have to be retrofit at all, or maybe that number is 0.4. Right now, we just don't know, but we do know that the ones with higher ratings have a higher risk of collapse, the kind of collapse that will kill people. So once the owner had these values, they could further evaluate or mitigate the risk from the inventory by starting at the highest ratings, most risk, and ask the owners to retrofit the buildings. Now, right now, the retrofit standard is in fact ASE 41. So they would be doing another analysis before they retrofit. And in some of those cases, the more sophisticated nonlinear analysis of ASE 41 might show that the risk of the building was actually less than this simplified procedure. But we're pretty convinced that the ratings like 0.7, 0.8, 0.9, that's never going to happen. But over time, it would work through the lower rated buildings. And again, when you get down to the 0.3 buildings, it might be shown that almost every time you do a more sophisticated analysis, the buildings are okay and maybe don't need to be retrofit at all. Most of these ordinances have very long time periods. So if you did set up a priority, it might be 10, 15 years from now before we ever got to the lower rated buildings. The way things go in structural engineering, there may be better analysis methods that will more clearly show that these lower rated buildings really don't need to be fixed. As I pointed out, other factors such as occupancy and building populations could be integrated, into these priorities. So again, to summarize, what are the uses? What were the intended uses of the methodology? It was primarily intended to rate individual older concrete buildings with respect to the risk of story collapse. Again, juries wanting to set priorities for mitigation of life safety, and owners of inventories of buildings wanted to understand the relative risk of each building. It also provides a method for engineers to differentiate between buildings that may fail consensus standard criteria. For any of you who have done a lot of ASE 41 evaluations, if it fails their criteria, the question is always, how bad is bad? I mean, there's no way to definitively tell that by running an ASD 41 analysis. So this might provide an analysis, a method for engineers to superimpose over a ASC 41 analysis and determine if it fails, is it just on the border or is it really bad? I already know of engineers who are in fact doing this, because once you have done an ASE 41 analysis, in many cases, you have many of the parameters that it takes to run a P-2018 methodology. Now, unintended consequences, this might suggest a format that the consensus pass-fail standards, i.e. ASC 41, could use to incorporate probabilistic variations in projecting performance. Right now, ASC 41 does not have a probabilistic performance. There are some probabilistic aspects to it, but it is not an overall probabilistic methodology. So in our opinion, P-2018 is kind of the first time that probabilistic methodologies have been used to actually look at a global performance rather than a performance of individual beams and columns and walls. So thank you for your attention. It's been quite a haul, and there's a lot of information we've given here. But I encourage you to pick up the book and maybe thumb through it, and you'll come to a better, more detailed understanding.
Great, thanks, Bill. So on behalf of FEMA and the Applied Technology Council, I'd like to thank Bill and Abbie for their fabulous presentation today. And I'd like to thank everyone in the audience for joining to learn about FEMA P-2018. So for those of you who are eager to receive your PDH certificate, note that they are only provided for those who registered and participated in the webinar. So if you're watching the recording, you are not eligible for a PDH. You can expect your PDH certificate within the next 4 weeks. And I would like to note that due to the large volume of participants that we have on these webinars, we cannot make exceptions to our PDH policy. So we appreciate your understanding on that. If you have a question that you haven't submitted yet, please go ahead and type it into the Q&A portal. We will keep the webinar open a few extra minutes in case you need more time to type in your question. Abbie was able to respond to some technical questions during the course of the webinar, but there are a lot more that she wasn't able to get to. So if you didn't get a response, please know that you will receive a written response via email within the next 4 weeks. There will be a survey that pops up when you leave the webinar. We really appreciate your input on the topics that you'd like to see covered in future FEMA webinars. We do use those statistics to plan our webinar program for the upcoming year. Lastly, you can expect a follow-up email with links to the recording, handouts, and the survey. So keep your eye open for that. And with that, we'll conclude the webinar for FEMA P-2018, brought to you by FEMA and the Applied Technology Council. I hope everyone